Welcome back. In the last video, what we studied was how we can use AFM to get a topographic picture of a surface. So 3 dimensions, structure, but no chemical or materials property type information. That is something we may very well want to understand, what's on the surface. And what's on the surface can be revealed both by material and certain chemical fingerprints that we're going to examine during this lecture. So the focus is now more extracting material types of properties. So if you remember, we finished the last video with this image where we saw this very, very high relief topographic image. These are minerals sitting on in a paper coating. And then we looked at this second image, which is taken simultaneously, but which has no topographic information whatsoever. And the question we ask is, what is this image? Okay, in fact, it's the same image, and what we can see is some dark regions here, which are characteristic of polymer, which is hiding in the crevices that we can't see in this topographical image. But over here, we can come down into these little gaps, and we see traces of the polymer, which is used to essentially stick the coating together. So how do we generate that image? Right, we'll look at a few different, this is an example of a few methods that we'll look at briefly in this lecture. There are others, and we'll even sneak in a couple of things that aren't on this slide briefly as we go. But let's start with phase imaging. Phase imaging has been around for a long time, and one of the reasons it is very heavily used is because we essentially get it free together with tapping mode. And when I say free, it's not that we don't have to pay for it, it's just that we don't really have to do anything else to the experiment. So I say both it and this slide have been around a long time, as you can see, but I think this encapsulates the flavour of what's going on quite well. Once again, we're using a laser beam here to detect the movement of our oscillating surface, which probably doing some tapping mode while on the other channel. But what we see is that there is a phase lag between the signal that we're using to generate the oscillation of the cantilever and the signal that we're measuring via the photodiode here. So that phase lag gives us information about the material properties of the surface. In general, I think it is fair to say that it does not give us quantitative information. It gives us a qualitative means of distinguishing different regions on the surfaces. So we can distinguish between hard and soft, but we probably can't put elastic moduli on the numbers. So as this oscillating tip comes over an area which is, say, softer, we see that the phase difference between the signal generating the oscillation and the measured oscillation increases. So what influences the phase shift? Well, the important properties for us are the viscoelastic properties of the surface. The tip comes down, has to sort of squidge the surface, so its movement is dependent on the viscoelastic properties of the surface moving under it. There may well be adhesion between the tip and the surface. That will depend on the material, the shape of the tip as well. And that will further influence the phase lag between what we measure and what we drive with. And once again, we have to worry about things like the cantilever characteristics, resonance frequency, and so on. And we probably also have to think about the tip surface contact area. It may be for a soft material that we're penetrating more. So all these things essentially determine the contrast in our image, and they also make it pretty difficult to extract any quantitative information. But 9 times out of 10, we don't need that quantitative information, particularly if we actually know what materials we got in the sample, and we just want to know how they're distributed. So here's another example. Here we have a height image. This is a vinyl acetate ethylene latex sample, and you can see these very bright features here on the surface. They correspond to surfactants, polymers that are just separated on the surface. We can think of this as a paint film, quite simply. And as the paint dries, these materials get left on the surface. So they're sticking out. You can see they're above everything else, so they're quite high. But that's just what we get from the tapping mode. If we look at the phase image, we can see how the two different polymers which are involved in this paint are distributed. We get these blocky domains which are hard and soft, and which correspond to the different materials. And if you look closely at the image here, you can actually see that around the different domains, you can still see those surfactant and polymers, which were very clear in the height image, but there was no evidence of the different polymers in the height image because we've got a nice smooth surface. But clearly, these surfactants and polymers actually aggregate at the boundaries between the different polymer domains. And if you're in the business of designing paints, that's the sort of information you want. And particularly during the 90s, the paint industry were churning out images of their samples and learning a lot about how to make them. This is a polymer blend. Again, the height image on the left doesn't tell you very much about the composition and where the different polymers are. You get a sense of the topography. You can see these little white spots, which once again are probably little contaminants of some description. But once you go to the phase image, where you have a contrast between the material properties, you can see this beautiful dendritic structure. And we can actually learn a lot about the way polymers crystallize and so on by looking at the surface in this fashion. And often the images that you generate are actually extraordinarily beautiful. Here's yet another example of literally watching paint dry. Once again, the left-hand image height tells us very, very little. And if you want a paint surface, if you designed your paint correctly, you should get a nice smooth surface. So the left image, I guess, is what you want to see from height, but you don't get any real understanding of what you're looking at. If you look at the phase image on the right, you see once again this fantastic dendritic structure, which is due to surfactants which have crystallized on the surface. So when you make a paint, you have to stabilize the polymer particles that the paint is going to consist of. And you often use surfactant to do that, and additives. And then as the paint dries, the polymer all sort of fuses together into a film, and the result then is that the smaller molecular weight molecules just get pushed out to the surface where they crystallize like this. And you might need to think, if you're in the paint business, about what that does for adhesion, for example, with the next layer of paint that you're going to slap on there. So here's an example that shows how choosing the force that we use to tap is quite important. So once again, a polymer, and here we can actually see the evidence of the polymer particles in the height image. So the polymer hasn't sort of fused together completely into a smooth film. But if we look at the phase image, we see really very, very little structure whatsoever. So it's pretty boring, which would indicate that we have a homogeneous material. But we know that the polymer is not homogeneous. We know there's different things in there. So how do we interpret that? Well, what we do have is obviously then a thin film coating the surface, which actually has, which is continuous. So in that case, then the way to try and detect subsurface information strictly. So that really means that we're not limited to the absolute surface with AFM. We can detect subsurface properties. So we take our cantilever and we just tap a little bit harder onto the surface, so we're pushing more as we go in. And that's enough to then bring out the inherent contrast in the image, and we can see then where the different hard and soft polymers are located. And you can see these big topographic blobs here, which are showing up as white images. They correlate to this softer material here, the brown polymer in the image. So we can see, get a very, very good feel for how the different components are distributed in the polymer matrix. Okay, so that's a very, very brief introduction to phase imaging. It's definitely one of the workhorses of the AFM armory. Force modulation imaging is perhaps not used so much now. It essentially combines tapping mode and contact mode, if you like. So rather than staying off the surface and tapping, it actually involves sliding along the surface, but oscillating the cantilever while in contact, and then looking essentially at the damping properties of the surface on the cantilever. So softer materials will damp the vibration more. And that's what you're using then for feedback and resolution. And once again, another example from paints. They lend themselves very well to these sorts of examples. On the left we see the height. On the right we see a force modulation image. The surfactant phase in this case is darker, which in this case correlates to a harder material. But we see that we can associate material properties with the topography corresponding to the surfactant. So there's very, very clear correlation between these two images, and we can understand the relative hardnesses. I mentioned before that when you make paint and you paint a surface, what you start with is actually, with a modern water-based paint, a suspension of polymer particles which you coat on a surface, and then as the paint dries they're supposed to fuse into a continuous film. So all the polymer particles fuse into a continuum. And this process in this case has been followed using force modulation spectroscopy, looking at latex surfaces which have just been successively cured at different temperatures. The higher temperature you have, obviously the easier it is for the polymer chains to interdigitate and for the spheres to diffuse into a continuum. So this is at 23 degrees, and when these images were taken, essentially you could not perform the thermal treatment in the AFM. You took your sample, heated it up, and then put it in the AFM and had a look at the effect of that. With modern techniques, and with, for example, the instrument park that we have in our department and down at Albanova at the Centre for Dynamic Nanotechnology, we can actually heat in situ now. So these experiments could have all been performed in situ during basically over a day, instead of being the much longer process that it was at the time. We would have got the same information essentially. So as I said, we can actually now heat AFMs from up to about 100 degrees. Some of the specifications go much higher than that, but there are certain questions then about what the effect on the cantilever and the electronics are of that high temperature. So here you can see in this image we've got both the height and the force modulation, so we can see here the structure of the polymer particles. They're still individuals, and we can see their material properties against the background on the right there. At 65 degrees, we see that the height image is now quite smooth, which tends to suggest to us that we've fused the particles and we've got a nice homogeneous film. But this is actually where the force modulation reveals more information. You can see that the structure is still just basically visible. You can still see individual particles and joins between the different regimes. So that indicates that while we may have on the surface got fusion, just below the surface the polymer hasn't completely fused. But by heating it up to 120 degrees, we can see that essentially we get the same information in both the height and force modulation image. And at that point, the polymer particles are no longer individuals, they're all part of a continuous film. Obviously, if you're designing a paint, you would prefer not to have to heat it to 120 degrees. All right, so that gives us a sense of material properties. But sometimes we actually want to get information about the chemistry of the surface. And in general, the AFM is perhaps not the primary tool for that sort of information, but we can nonetheless extract some important chemical contrast of the surface. So let's talk very briefly about how to probe chemical information with AFM, and we'll talk primarily about lateral force or friction force microscopy. Adhesion is quite an important giveaway. Force volume imaging is a technique which has traditionally formed part of this armory, but over the last 3 to 4 years, this being 2014, that technique has been superseded by a host of far more high-resolution material properties imaging techniques, which we'll discuss instead. So one way to achieve chemical mapping is to actually look for specific interactions. And one route you have to accomplish this is, rather than just use a tip out of the box, is to coat the tip with a specific chemical, indicated in this case by these little blobs. And then you rely on the fact that at the chemical level there's either specific interactions, maybe hydrogen bonding interactions between these blobs, and Y and I on the surface react differently. Maybe one hydrogen bonds, one doesn't. Let's say we have a carboxylic acid probe and we have an amine here and just a hydrocarbon here. Then our intuition tells us that we should get a chemically rather different interaction between physical chemically rather different interaction between the probe and the surface. And we're looking then to generate some sort of contrast, as we see here, by using this chemical force, using a functionalized probe. So we could look at adhesion. To do that in general, we actually, at each pixel, we have to come into contact and then come out again. So it's a bit more demanding in terms of instrumental time and so on. So another way to do it is just drag the tip over the surface. So essentially go back into contact mode and measure the friction. And that's what we have with lateral force microscopy, which you can see illustrated in this slide. As the tip slides over a region of different frictional coefficient, indicated by the red, the cantilever twists. The cantilever is going to twist. And if we've designed our photodiode correctly, it's not only going to be sensitive to vertical deflections of the cantilever, so up and down, it's also going to be sensitive to twist of the cantilever. So we can use the twist in the cantilever as another force sensor in a different plane to understand the chemical interaction between the tip and the surface. And you can see the spot here moving across the photodiode in response to the different frictional force on the surface. So here, rather than having the contrast given by the topographic height, it's given by the frictional force. But because we're doing it in contact mode, we can actually extract the height at the same time. So we can get multiple information. So here's, once again, a vinyl acetate ethylene copolymer. The left-hand image is the height image. The right-hand image is a friction image. So you can see that there is the features that you see over here in the topography. They're not just topographical aberrations. They actually reflect differences in the chemistry, because you can see that the frictional force is different where the height differs. And that means that we're looking at things of different chemical nature there. So by looking at that image, we're not going to say what they are. So with an XPS, we can say what they are. All we can see is that there's a chemical difference. So we do rely on having some knowledge of the properties of the material. Another example is a tool steel. So that was before it was a soft polymer. We can equally well do this with a hard material like a tool steel. So what we're looking at here, I think we've reversed the images in this case. The right-hand image is the height image, and the left-hand image in this case is the frictional force. And this is a fairly novel tool steel, which is designed to be harder, stronger, resist corrosion, and so on. And what you can see is that the white areas, which are the high areas, also correspond to lower friction, which is of course exactly what you want in a tool steel, because as you're cutting the material, you want to minimize the sort of burring and scarring of the surface that you're cutting. But you can see that, once again, as we look at the surface, the structure here, we can clearly see that these topographic aberrations or asperities, which are in fact hard phases embedded in the steel matrix, in which this case have a high nitride content, they're proud from the surface, and they are obviously chemically very different. And it turns out that that chemical difference leads to a benefit in the material properties in this application. This, to me, is perhaps one of the most powerful examples of lateral force microscopy. It's the same image taken in different scanning directions. So in the left-hand image, I can't actually remember which way the travel is. Let's say that the tip is moving in this direction. Whereas on the right-hand image, let's say the tip is moving in the other direction. And in both cases, we're measuring the frictional force, so the twist in the cantilever. But we're sensitive to, in this case, the molecular orientation of the species. So why are we getting this beautiful contrast, and why is it reversed? Well, if we were to look at the height image of this image, we would see absolutely no topography at all. This is a completely smooth structure, and it consists of phospholipids. But as the tip slides over the surface, it's actually sensing the orientation of the alkyl chains attached to the lipid. So they're not sitting vertically out of the surface in the different domains that you can see there, and we're revealing, obviously, that there are domains within this apparently homogeneous film. And it's analogous to the nap on a billiard table, or indeed on the surface that we have here, that rubbing your hand in one direction gives you a completely different friction than in the other direction, because it depends on which direction the fibers are oriented. So that revealed a wealth of structural information that would have been absolutely inapparent by any spectroscopic techniques or by topographical imaging. While we're on the subject of friction, we can actually get a little bit more advanced than just looking at the lateral force. Typically, the friction coefficient is the material parameter that characterizes whatever it is you're looking at, which is the gradient of the frictional force against the applied load. So how big the frictional twist is as a function of how hard we push the surfaces together. So in the previous images, we had a single applied load, and we were just measuring the friction and looking at the differences in the two regions. What we can do is take a series of images at different applied loads, and then we'll see that the friction varies with that applied load, and we can tile those images so that they sit on top of each other in space, and then at each pixel we can actually see how the frictional force varies locally with the applied load, and extract pixel-wise the friction coefficient for that point. That gives a little bit more information about the materials, and certainly gives us better feel for the properties of that material. And it's perhaps worth noting that from that technique we can also, as a sort of a freebie, extract the adhesion at that point between the tip and surface without actually separating the surfaces, which is an interesting little twist in that, which I think is the only means of doing that. And the argument can be raised as whether it's a reasonable measurement of the adhesion. Okay, now I think it would be wrong to not mention the fact that we can actually perform quantitative friction measurements at the atomic scale here. It's not necessarily something we would use for material characterization, but the AFM has revolutionized our understanding of tribology, which is the understanding of friction, lubrication and wear, particularly for interfacial friction. So if we take an AFM tip at very, very high resolution and slide it over a surface, we can actually measure the atomic stick-slip events associated with that tip being slid over the atomic features of the surface. And if you look at the top of these rather small images, I'm afraid, you can actually see a tip sliding over graphite in air, and the corrugations in this image sort of give us a feel for the local stick slip as we go over the lattice. This is another example where we then added ionic liquid to the system. And one of the interesting things about ionic liquids is that you can, by controlling the potential that you apply to the graphite surface, you can actually choose which molecules, or which ions I should say, are on the surface, or their relative populations. So as you tweak the potential, what you can see is you can control the amount of this stick slip, and the hysteresis between these, the curve sliding in this direction and then turning around and sliding back in the other direction, is also a measure of the work you have to do and the inherent frictional hysteresis of the system. And it's worth noticing that by choosing the right potential and then thus choosing the right ion on the surface, that by sort of matching the adsorbed ion to the surface, you can eradicate basically the frictional dissipation altogether. So this has a vanishingly low friction coefficient. It's referred to as superlubricity, a friction coefficient of 0.001 or less, which is very, very low. Whereas a typical interaction of my finger with the surface, for example, would be about 0.3, to give you a reference. So there's a lot of fundamental understanding in the area of friction and tribology that can be generated with the AFM. All right, so the other thing we have is the adhesion. That's a very characteristic measure of the interaction between a tip and a surface. We should be a little bit careful if we're working in air, because as I mentioned in an earlier lecture, you can get water condensation around the tip in contact with the surface, and that the presence of that water is also going to affect the adhesion. So in some cases, you completely lose adhesional contrast as a result of the fact that your contact is always the same, because it's determined by the water film rather than the material properties. So let's just sort of in our head get an idea of what we're doing with an adhesion measurement with the AFM. So let's think of our spring cantilever now as a coiled spring. We bring up our surface towards it. As the surface approaches, in general what we'll see is that the spring expands towards the surface because there's an attractive interaction. Then we come into physical contact. We maybe continue to drive the surfaces together, so we maybe constrain the spring a bit more. Then we turn around and we start pulling the surface away from the tip. And we can see that as a result of the adhesive force, the spring expands and remains in contact even beyond its equilibrium position here. So on the way in, there was no contact here. On the way out, we're still in contact. So we're getting a large deflection of the spring before the energy in the spring, stored in the spring, overcomes the adhesion, and the surfaces are then allowed to separate. And typically what we will see in the AFM, if it is a large adhesion, is we will literally see the twang, that we'll see the AFM oscillate in response to the rapid release of the adhesive interaction. Now, as I mentioned before, chemical force volume mode, I beg your pardon, and that's been replaced now. One of the things that's replaced it is something called peak force, or quantitative nanomechanical mapping. And this is a technique whereby at very, very high frequency we perform a force curve at every pixel on the surface. And rather than using an oscillation of the tip to do that, we actually move the piezo or the surface towards the cantilever and measure the interaction at each pixel and make the image in that way. So you can think of it as a very, very high-speed static measurement of the force, rather than extracting it from the dynamic data as we did in the example of Susie Jarvis' phospholipid study in the previous slide. Now, the way the software works in this example is that it analyzes the force curve as we see in this example. So just remember, here we're out of contact, we come into contact, we experience towards contact, we experience a small attractive force in this case, and come into some sort of physical contact at the tip and surface. And in this region we're compressing the surface, we turn around, we come out, the adhesion means that we don't follow the same path, and we get to some sort of point where we eventually snap out of contact. So the minimum that we achieve on our way out is a measure of the adhesion. It's a measure of the adhesion. The adhesive energy we should probably strictly define as the area between the outer curve and the baseline. But in this case, it's defined as the minimum, and instead we have this term called the dissipation, which essentially describes the area between these two curves, which is essentially the dissipation, which is a strong function of the material property, the viscoelasticity. It's possible to fit contact mechanical theories, which we're not going to go into, but essentially the contact mechanical fitting allows us to extract a measure of the elastic modulus of the surface. And all this happens in real time at each pixel, and then the software throws away the force curve and retains the parameters that it's extracted from the force curve. So we get a whole host of images from a single scan, or a host of different parameters that we can use to provide contrast on our surface from a scan. So the elastic modulus is one, adhesion is another, and these are both respectively material and chemical type information. Dissipation is also, and deformation are both also indications of the material properties of what's underneath the tip. But we should also be aware that the elastic modulus and the deformation are extracted from the same data. Now, one of the tutorials, Ralph describes the fact that when polymers solidify, that even if you have two quite similar polymers, they will locally phase separate as much as they can. Here's a very nice peak force image that indicates just that. So here we've just got polymers sitting on a mica substrate, and you can see there's a very, very clear, you can sort of essentially follow the polymer chains and their segregation very, very clearly in this image. You can see one sort of contrast is the height. We get the elastic modulus of the materials, and we can also see how the adhesion varies. So from these parameters together, we actually get quite a good evaluation of the surface and how the molecules are distributed. Okay, now I mentioned earlier that at KTH we have something called this multi-frequency AFM, often known as intermodulation mapping. And this is a technique that was developed by David Haviland at KTH, which you can think of as being an alternative to the technique which I just mentioned. And this is very much a dynamic rather than a quasi-static evaluation of the surface. And this, if you want details of this, you have to ask David. But I'll give you the easy version, which is the limit of my understanding. So instead of oscillating the cantilever at a single frequency, you oscillate it at two frequencies. And when you're free from the surface, you can see these sort of two peaks here. And we get these two very well defined peaks. However, when this oscillating or bi-oscillating cantilever comes towards the surface and starts to interact with the surface, but prior to contact, what happens is that we get this very nonlinear response, and we get these so-called intermodulation products that we can think of as interference peaks associated with the oscillation. And because we get different amplitudes at different frequencies from a single oscillation, it's possible to extract an entire force curve, that is to say, the tip surface interaction as a function of distance, both for conservative and dissipative forces. And of course that's exactly what you want for nanomechanical processing, and you don't actually have to do a physical force run to achieve it. So here's an image sort of showing the sort of contrast that you can get, and in this case it's nanoparticles or microparticles coated with a protein, which sample that comes from Per Claassen at Surface and Corrosion Science. And David's applied his intermodulation technique to that. You can see the topography, but then from this dynamic interaction, he's extracted the force profile, the interaction of the surface with the tip as a function of separation, which you can see in the red and blue curves here, which correspond to these two different points on the surface. And you can see that there's a different adhesive interaction or attractive interaction here. And he's then used the magnitude of that adhesive interaction, which is extracted, or attraction, which is extracted from the interaction, as the contrast. So he's superimposed that adhesion information on the topography, so you can see how that chemical behavior is varying spatially. So once again, very, very powerful, means of extracting both chemical but also materials properties. Here we've got a polymer sample, which is PMMA, PDMS, PDMS being the softer one. And in this case, from the dissipative component, which you extract from the intermodulation information, you can sort of essentially plot the materials variation across the sample. So the different colors in this image reflect regions of sort of different hardness. And if you apply the same sort of DMT analysis or contact mechanical analysis to this interaction, you can equally well extract the modulus of the different regions. So you get local nanomechanical properties. And the good news from David is that, of course, you can upgrade your existing AFM with his technique. You don't have to buy a new AFM. It's something that can be applied pretty much to any AFM if you want to achieve this sort of nanomechanical information. So we're just going to round off with a little video, which to me is, well, this is one of the most powerful things I've ever seen. This is a video rate AFM. So this is a guy in Japan whose name is Professor Toshio Ando, who has essentially the only person who can yet do this, but he's designed AFMs that can scan so rapidly that they can actually take images at video rates. So he can. I mentioned before that a frame usually takes us of the order of minutes to generate by scanning the surface, the tip over the surface. He can perform scans on the order of milliseconds, which means he can watch molecules moving in real time as long as he doesn't manipulate them. And this little example, which I have shamelessly downloaded from his homepage, shows a myosin molecule actually walking along an actin fibril. So we're actually able to not only see these things, we're actually able to follow their biological activity in real time. And to me, this heralds a new era of nanotechnology.